Hello, my dear students. Welcome you all to today's session in the Teacher app, the Teacher platform, a best learning platform. I welcome you all for today's session that is a special and the most wanted session that is organic chemistry. If you have listened to the last previous videos, we were discussing the preparation of haloalkanes and haloarenes from alcohols, right? Let's continue today's session also, which are the various other methods for the preparation of haloalkanes or haloarenes. So once again, I welcome you all my dear second PUC science students. I welcome you all to this the best platform that is the Teacher app. So, uh, let's continue with the methods of preparation of haloalkanes. That is gonna be very easy methods, and uh, we can adopt the different types of compounds. For example, now in front of you, a slide what you can observe is alkene. You all know what is alkene, right? It is nothing but double bonded hydrocarbon. So by taking alkene also we can prepare haloalkane. So how can we prepare haloalkane by taking alkene? So students, are you able to observe an example that I have put in front of you in the slide? So take any alkene for example. Let me take alkene as in general. I'll be writing alkene as C double bond C, and you know that each carbon atom contains 4 bonds, right? Let me take a simple example that is ethene. So what is ethene? Ethene is nothing but CH2 double bond CH2, right? To ethene, let me add any hydrogen halide. Students, what is hydrogen halide? Hydrogen halide is nothing but it can, for example, you can take hydrogen chloride or hydrogen bromide or hydrogen iodide. So any type of hydrogen halide, for example. So treat alkene with any type of hydrogen halide. For example, if I take hydrogen bromide, what happens? A bond breaks, you know that a bond, a pi bond is very easily can be broken when compared to, that means the pi bond undergoes cleavage very easily compared to sigma bond. Now if this is a sigma bond and this is a pi bond, so this cleavage of the pi bond is easy. So here also a cleavage of bond between hydrogen and bromine takes place, and what you have to do is very simple, my dear students. Add this hydrogen, that is H plus ion, to one carbon atom and Br minus ion to the another carbon atom to satisfy the valency of carbon atom, that you know that each carbon atom must contain 4 bonds. Therefore, already it was CH2, right? So what I did, I added one H plus ion. The hydrogen will form a bond with the carbon atom. So now see, this first carbon atom is satisfied with 4 bonds. It is attached to 4 other atoms, right? Now same way to the next carbon atom also, the halogen, that is the bromide ion, forms bond with the next carbon atom. And what you get here is, yes, definitely it is nothing but haloalkanes. This is a simple trick or a simple method that I explained with you. So what type of haloalkane you got? What you had taken is ethene, right? It was ethene, and what I got, the product is, yes, it is bromoethane, right? So this is a method of preparation of haloalkanes. The same way, here I put in front of you one of the best methods. See, what does this indicate? See, this end indicates one carbon atom here, also one carbon atom here. Haloalkane in general, sorry, hydrogen halides in general, it is represented as HX. So what you do? So add one hydrogen forms bond with one carbon atom and halogen forms a bond another carbon atom, and you get different types of hydrogen halide. So let me put an equation one in front of you. So I want you all to predict the product. Okay. For example, if I had taken propene, that is CH3 CH double bond CH2. So what is this? You all are familiar, right, students? The example that you have I have put in front of you is nothing but propene, right? So what you do to the propene, you add hydrogen halide. For example, here I take hydrogen iodide. So tell me the product. What happens here, dear students? Can you predict the product? Yes, here, as soon as I tell you have to add hydrogen iodide to propene, you will be thinking that you have learned this somewhere, recalling the concept what you have learned, right? Yes, this follows a rule, the special rule, and most of you know what it is. It is nothing but it follows Markovnikov's rule. Yes, it follows Markovnikov's rule. You have to follow when you have taken unsymmetrical alkene. So whenever you have taken example of unsymmetrical alkene, follow Markovnikov's rule. If you have that you have studied in your first PUC level, if you have forgot what it is, once again a simple trick I will tell you to understand Markovnikov rule. You know that if it is a hydrogen iodide, a bond breaks between the cleavage of bond between hydrogen and iodide ion takes place. How to add this hydrogen iodide to propanus, dear students? What you do is just add hydrogen, is the two doubly bonded carbon atom, right? So what you do, add hydrogen to that carbon atom containing highest number of hydrogen, and add the halogen, that is iodine, to the carbon atom that is containing the least number of hydrogen. So you should always add the negative charge, that is I minus, to that carbon atom containing least number of hydrogen atom. Is that clear? So I will write the product here. Look here, students. So the product will be what I did. I will add the negative charge, that is the iodine, the halogen, to the carbon atom containing least number of hydrogen atom. So here the pi bond is broken, and what I get, and I added the hydrogen to the carbon atom containing highest number of hydrogen. So therefore the product will be what it is. The product is nothing but 2 iodopropane is the product what you got, right? Understood? When it is symmetrical alkene, it is very simple way of adding hydrogen halide, but when it comes to unsymmetrical alkene, you have to remember, you have to follow Markovnikov's rule. Is it clear, students? Yes, I hope it is clear for you all. Let's move on to the next way of preparation. Here also what we do is we are taking alkene only, and addition of halogen, not through hydrogen halides, but here I am going to take directly the halogen atoms. You know that the halogens always exist in diatomic state. For example, Cl2, Br2, so I2, like this. Halogens that exist in diatomic state, I can add these halogens directly to the alkenes, but it happens in the presence of non-polar solvents like CCl4, either carbon tetrachloride or carbon disulfide. These are the non-polar solvents which are very good solvents to add halogens to alkene. So here also, for example, if I take a simple example like C double, in general I will explain you. In general, if I write alkene like this, add any halogen, for example, bromine, in the presence of carbon tetrachloride, what happens? We end up getting the product vicinal dibromide. You can see in the slide also. Just what you do, so bromide ion, that is nothing but bromine, exists as Br2, right? Just add one halogen to one carbon and the another halogen to another carbon. So it will be, so what happens? What you get is Yeah, you can call it as 1 comma 2 dibromo. Yes, it is 1 comma 2 dibromo, dibromoethane. Students, otherwise very simple way I can call it as vicinal dihalides. In general, vicinal dihalides, and especially this is vicinal dibromide. What is vicinal dibromide? It is nothing but two halogen attached to the uh, two carbon atoms that is nearby, that is for example, you can see here two halogen atoms that is attached to both the carbon atoms. It is two carbon atoms, then it is called as vicinal dibromide. Is that clear, dear students? So very simple way we can use alkenes in the preparation of haloalkanes, right? So very simple to understand. So we understood that if we have alcohols, using alcohols we can prepare haloalkanes, and if we have alkenes with us, using alkenes also we can prepare haloalkanes. The same way, yes, the same way we'll come. We are going to the next important method, that is halogen, especially known as halogen exchange method. Okay, so this halogen exchange method is very interesting and a very important method of preparation of haloalkane. That is the first one I'm going to explain you is Finkelstein reaction. This is one of the uh, important naming reaction in the preparation of haloalkanes, my dear students. Okay, it is the name of a scientist who did a research on preparing haloalkane using this method. The scientist's name will be given to the particular reaction, that is known as Finkelstein reaction. So this Finkelstein reaction can be used to prepare specially iodoalkanes. So whenever I need to prepare iodoalkanes especially, I can go for Finkelstein reaction. Okay, so when we will use this Finkelstein method of preparation, whenever I need to prepare iodoalkanes, I can go for this method of preparation. Take any haloalkane, like either you take chloroalkane or you take bromoalkane. Okay, I have chloro or bromoalkane with me, but what I require is iodoalkane. So what I do, very simple, that I'll just treat this chloro or bromoalkane with sodium iodide, a well-known reagent, that is sodium iodide, in the presence of what? In the presence of, dear students, we use dry acetone. Acetone is nothing but the first member of ketone. A dry acetone will be used as a catalyst. Why I have to use acetone? What is the role of acetone? Yes, I'll definitely tell you later. So let's see what happens in the reaction. Very simple. It is just a simple substitution reaction, dear students. What you do? Break the bond between alkyl group and chlorine and add iodide ion to that, and what you get is Ri plus NaCl, right? Same way. So here also what I did, I will take any bromoalkane I have with me, treat that with sodium iodide in the presence of acetone. So what happens, dear student? It's nothing but I will get alkyl iodide plus sodium bromide, right? Understood? The simple substitution. Therefore, this is known as halogen exchange method. Now, what is the role of dry acetone? So, I require only iodoalkane. I don't require this byproducts like NaCl and NaBr. So, what do I have to do? I have to remove this byproduct. So, when I use this dry acetone, this acetone will precipitate out or it helps in the removal of this byproducts. Is that clear? A very simple, very easily understanding Finkelstein reaction. You have to practice this by taking more and more examples, right? So if I need to prepare iodoalkane, immediately I will go for Finkelstein reaction. Then what if I need to obtain fluoroalkanes, right? So I have to prepare some of the fluoroalkanes like CH3F fluoromethane, or if it is C2H5F, it is fluoroethane. So I have to prepare this kind of haloalkane. Then I will go for one of the important and the best method to prepare fluoroalkane is Swarts reaction. This is also a naming reaction, well-known method to prepare fluoroalkane, that is Swarts reaction. So in Swarts reaction also, my dear students, what you have to do is you have chloroalkane or you have bromoalkane. Just treat that with silver fluoride like AgF or mercurous fluoride or any type of metallic fluoride salts. Is that clear? For example, see a simple best example is given here. What they have did is they have taken CH3Br. So what is the CH3Br? It is nothing but CH3Br is bromomethane. Now what I do? Bromomethane I will treat with silver fluoride, right? So now as usual, as I told you in the Finkelstein method, the same thing you can follow here. That is just a halogen exchange can take place and you can get CH3F, that is fluoromethane, plus silver fluoride is now turned into silver bromide. So what is the product you got? So you got fluoromethane, right? For one more example, I will explain you using, for example, other metal salts. Like what if I take mercurous fluoride? Okay, this with AgF for silver fluoride, it is very easy to understand. That is just a halogen exchange takes place there. Also, let us take, for example, I have taken ethyl bromide C2H5Br and treated that with mercurous fluoride Hg2F2. So what I have to do here is, dear students, just balance the equation. Mercurous fluoride contains two fluorine atoms. So what you do, I'll take two molecules of bromoethane here. So I will get the product two molecules of C2H5F plus Hg2F2 is now turned into mercurous bromide, that is Hg2Br2. And what I got here is, yeah, yes, it is fluoroethane. Is it clear, my dear students? So this Finkelstein reaction to prepare iodoalkane and the Swarts reaction to prepare fluoroalkanes is the best known halogen exchange methods in preparation of haloalkanes. And now, yes, we will come to one of the most important and most interesting reaction to prepare haloalkane, my dear students. That is Sandmeyer's reaction. So, have you heard the Sandmeyer's reaction anywhere before? Students, the Sandmeyer's reaction you also study in the last organic chemistry chapter, that is amines. Okay, the last organic chemistry means also, yes, after that there are some common concept, common chapters like biomolecules, polymers, all that. But the organic chemistry, especially the last chapter, that is amines, there also you come under the Sandmeyer's reaction, and also in haloalkanes you study this. Listen carefully. This is gonna be a very interesting reaction to prepare, especially what we can prepare in Sandmeyer's reaction. Through Sandmeyer's reaction is we can prepare haloarenes through Sandmeyer's reaction. Previous examples you saw the preparation of haloalkanes, and now through Sandmeyer's we are going to prepare haloarenes. Haloarenes means what? We can prepare chlorobenzene, that is C6H5Cl, or we can prepare bromobenzene through Sandmeyer's reaction. Okay. So here, as you can go through the slide, a primary aromatic amine dissolved in cold aqueous mineral acids and treated with sodium nitrite. See, we have to take a mineral acid with sodium nitrite. A diazonium salt. A diazonium salt is formed, and now mixing this diazonium salt with cuprous chloride or cuprous bromide, resulting in the replacement of diazonium group by Cl or Br. You can go through the equation, my dear students, here. So let me explain you this equation. For example, Sandmeyer's reaction, what I can do is I will take primary aromatic amine. Let me explain you a very simple way. What is this? Benzene ring with NH2 group. What is this called as, my dear students? So benzene ring with NH2, the an amine group in this, popularly known as, this compound is known as aniline. So what do we call this is primary aromatic amine. So primary aromatic amine is nothing but aniline. So how do you have to remember the Sandmeyer's reaction is, first you remember the reactant that we are taking. The reactant that we are taking is aniline. Now I will treat this aniline with sodium nitrite. Sodium nitrite means NaNO2 plus mineral acid, that is hydrogen chloride. So remember the reactant, and once you remember the reactant and the reagents used, easily you can remember the reaction. Okay, you should not at all by heart any reactions, dear students. As soon as you listen to the name Sandmeyer's, when you hear this reaction, Sandmeyer's reaction, what you have to do, you have to recall what is the reactant I take and what are the reagents I use, and immediately you can guess the product. Okay, so the reactant that I take in Sandmeyer's reaction is aniline, that is C6H5NH2, and this I am treating this aniline with a reagent sodium nitrite in mineral acid. So the sodium nitrite with mineral acid will, a mixture of sodium nitrite and mineral acid is otherwise called as HNO2, that is nitrous acid. Students, what I am telling is, what I take here, that is NaNO2, which is called as sodium nitrite, even with mineral acid, that is HCl. This mixture together is called as nitrous acid. Okay, this mixture is called as nitrous acid. Nitrous acid means what? Nitrous acid means nothing but HNO2. Fine. Now when this nitrous acid reacts with aniline, what happens is the NH2 group is converted to diazonium salt. What is diazonium salt? It is nothing but N2Cl, nitrogen with positive charge, chloride ion with negative charge. So what you can understand from this is the complete aniline group here, what you can observe, is converted to, from where this chloride ion you got from HCl and NaNO to the nitrogen ion. What you get, you the in aniline group, the NH2 group is replaced by N2 plus Cl minus. N2 plus is known as benzene. What is this N2 plus known as? Diazonium group. Diazonium, and the salt here is chloride ion. So the name of this compound is benzene diazonium chloride. Is that clear? Is that clear, my dear students? I know you will be getting confused how this NH2 group is suddenly turned to diazonium group. Yes, for that also there is a mechanism, my dear student. I will explain you the mechanism. But first let us conclude this Sandmeyer's reaction. Okay. So when I take this, you know that now you understood that NH2 group through the help of nitrous acid, it is converted to diazonium group. Here diazo means N2, nitrogen twice is known as diazonium, and the salt is nothing but chloride ion. So benzene diazonium chloride. So now what I do, take this benzene diazonium chloride that is formed, or benzene diazonium chloride that we prepared, freshly prepared benzene diazonium chloride, treat that with, that is N2 plus and Cl minus. When you treat this benzene diazonium chloride with cuprous chloride, again in the presence of acid medium, mineral acid, so here what happens, this diazo group, what I told, that is this N2 group is a good leaving group, my dear students. So in all the organic chemistry chapter, when you come across any reaction, if you see this N2 group, that is diazonium group, it is a best or good living group. I can tell you, living group means it leaves easily, it comes out easily. That's the meaning, good living group. So nitrogen can come out easily as a nitrogen gas. So and the chlorine, chloride ion Cl minus can form a bond with the chlorine atom, and you get chloro, benzene, and nitrogen comes out as a nitrogen gas. Is that clear? So what we prepared? We prepared chloro benzene, right? Now also, what happens if you take the benzene diazonium chloride and treat it with cuprous bromide, also in the presence of HCl, what you get is you replace nitrogen atom comes out as nitrogen gas. Yes, it is a good leaving group. It comes out as nitrogen gas. Here, the chloride ion will be replaced by bromide ion, and I get bromobenzene, and this chloride ion can come out with copper as cuprous chloride. Is that clear? So we taking the benzene diazonium chloride, we prepared chlorobenzene as well as bromobenzene. Is that clear, my dear students? Very interesting, right? The Sandmeyer's reaction. Yes. So I hope you all found interesting, and also you all are thinking how this aniline is converted to diazonium. Let me give a simple explanation. Hope you all will understand, and if not, you can take a screenshot of it and analyze the I will just write the mechanism. You can take a screenshot of it and analyze the mechanism further. Okay. And so what happens? I told you, you have to take the reagent, that is sodium nitrite, that is NaNO2, in the acidic medium mineral acid HCl. What it gives, this mixture is nothing but nitrous acid HNO2, right? So how do you write the structure of HNO2? Students, HNO2 is nothing but I can write it as HNO2. Is it clear? N double bond O, single bond OH is HNO2. And the oxygen atom will have a lone pair of electrons, as you all know. What happens? Uh, since the medium is acidic, this oxygen through its lone pair, it can grab a proton, or it can grab a H plus ion. So when it accepts or it grabs the H plus ion, what happens? HNO2, whatever I had HNO2, now it is OH2 plus. Is it clear? Because through one lone pair, it forms a bond with the proton. Is it clear, my dear students? Stepwise explanation of the mechanism for those who are thinking how this NH2 group is converted to diazonium group. I am giving this explanation, right? And also I told you, the N2 group is a diazonium group, is a good leaving group. The same way, students, wherever you find H2O, the H2O is also a good leaving group. So here what happens, you can see a bond breaks here, cleavage of bond, this part can go out as H2O. So when H2O is removed, what happens? The remaining is N double bond O, and Since the bond is cleaved between nitrogen and oxygen, nitrogen atom gets positive charge here. And what is this, dear students? This is nothing but N double bond O. This is called as nitrosonium ions. So what is this called? This is called as nitrosonium ion. Is it clear? Yes, it's clear. Now what I do? I will take this nitrosonium ion and treat with aniline. Okay. So take this nitrosonium ion and treat this with the reactant, that is aniline. Now you come back. What reactant we have taken? We have taken aniline. So what this aniline with the lone pair of electrons on the nitrogen atom will do? The aniline lone pair of electrons on the nitrogen atom will accept the nitrosonium ion and forms a compound like this. Observe. NH2. Yes, N double bond O, right? So I got the nitrosonium ion attached to the aniline. So now a proton, one H plus ion leaves here, and this bond comes as a lone pair on the nitrogen atom. Okay. So one proton is escaped. It leaves the compound. So what happens? At the bond there comes as a lone pair. So one proton is left. So what is left? NH N double bond O. Now what happens? This oxygen which has a lone pair will accept this hydrogen, because the O minus will be waiting for the H plus ion, right? So the nitrogen with its lone pair, what it does, it accepts, because what happens? So if this lone pair comes here as a double bond, immediately this lone pair goes as a negative charge, and that negative charge will be accepting the H plus ion. Is that clear? And so when that negative charge, observe here, dear student, now how do I write the product you observe? It is N double bond N OH, right? Just a minute. So N double bond N OH. Is that clear? Since a lone pair is gone, this will get a positive charge. Now, when this again, what this oxygen with the lone pair electrons will do, it will accept one more higher proton or H plus ion. So when it accepts one more proton or H plus ion, what happens? Whatever the OH group was there, it will now form OH2 through its lone pair. When it accepts the one more proton or a H plus ion, now it is OH2, and you all know the OH2 is a good living group, and this leaves the compound, and the bond comes here as a triple bond. Now what I have is diazo group on the benzene ring. Is that clear? Now what I have is N triple bond N, that is diazo group, and it will be waiting for the Cl minus ion that it gets from the HCl, the acidic medium, and you will get benzene diazonium chloride. Students, you can take a screenshot of it, and you can work out and go through the mechanism for a clear understanding. See, Sandmeyer's reaction, actually you don't have to write all these in the exam. Just understand Sandmeyer's reaction very well in this pattern. Okay. That is aniline, and treated with a nitrous acid mixture, you will get benzene diazonium halide, and this benzene diazonium halide, on treating with any cuprous halide, you will get aryl halide. And for the first step of preparing diazonium, I have given a mechanism which you can take a screenshot of it and go through it. Okay. And so in today's class, we discussed most interesting and most important methods of preparation of haloalkanes and haloarenes through halogen exchange methods like Finkelstein, Swarts, and also preparation of haloarenes through Sandmeyer's reaction. So it was very interesting, right? So these are some of the best methods of preparation of haloalkanes and haloarenes. And also this haloalkanes and haloarenes, my dear students, it will have or it will show very unique physical properties as well. Okay. So what are the physical properties or a unique properties this haloalkanes and haloarenes show is? Physical properties means, my dear students, under this we will study like physically or the appearance. What are the things that we can observe when we see this haloalkanes and haloarenes? Its color, its smell, its solubility, its melting point, its boiling point. These terms are known as physical properties. So let's discuss some of the physical properties of haloalkanes and haloarenes. So point wise, let's discuss. Yes, alkyl halides are colorless when pure. Yes, in pure form you take any haloalkanes like chloromethane, bromoethane or iodo or fluoro. Any haloalkane, yes, it will be colorless. So maybe some impurity or mixed with any solution, it may show different colors, but in its pure form, it is colorless. And yes, bromides or iodides develop color. That means when it reacts with light. Okay. And also when it comes to the odor or smell, it is having a pleasant odor or sweet smell, means not a bad or a very itching kind of odor. It is having a pleasant odor. Okay. And when it comes to boiling point and melting point, some of the haloalkanes, like we can call it as simple haloalkanes, they are gases at room temperature. That means, students, what happens? No, simple haloalkane means CH3 X or C2H5X. That means when the number of carbon atoms are very less, they will be in its, that is the beginning of the haloalkanes, the molecules will be in gaseous state. Whereas as the number of carbon atom increases like this, what happens? As the number of carbon atom increases, it will be in either liquid state or the solid state. So therefore, one point you have to remember, if in general, if I write haloalkane as CX, dear students, you know that between the, this is a carbon atom and this is a halogen atom. Between carbon and halogen atom is highly electronegative. Okay. Halogen atom is definitely highly electronegative. Therefore, I'm not telling when it ionizes or break the bond. I'm not talking about cleaving the bond. In the force of attraction, there will be a force of attraction here between carbon and halogen, right? So a bond is nothing but it is a pair of electrons, right? The electrons will be tilting more towards halogen, because therefore the halogen will be partially negative charge and carbon will be partially positive charge. So the partial negative and partial positive is denoted by this symbol. Partially negative, partially positive means the force of attraction, that we call it as intermolecular force of attraction, is very high in haloalkanes, because halogen, which is partially negative, since it is highly electronegative, it will try to attract electron towards itself and develop partial negative charge, whereas carbon will not able to try to attract electron more towards itself because it is a electropositive, so it will be having partial positive charge. Okay. So because of this partial negative and partial positive charge on carbon and halogen atom, we can say that it has greater polarity, polar in nature. Haloalkanes or haloarenes are polar in nature because a single compound has both positive and negative charge, and also force of attraction is more. Therefore, its melting point and boiling point also will be very high. Is that clear? Yes, definitely they will be having high boiling point. In that, the order goes like this. That is, alkyl iodide is having more boiling point, and then comes alkyl bromide, and then alkyl chloride, and then the last is fluoride. Why this increasing order? Why is this order? Because yes, students, what you're thinking is definitely correct. You know that the iodo alkene, the iodo group, the iodine, is bigger in size compared to bromide ion, right? So what happens as you move like this, the size decreases, right? That means you know that in the periodic table, when you come from fluorine to iodine, the size increases. Yes, as the size increases, the van der Waals force between, this is a force of attraction between the iodine and alkyl group, that is called as van der Waals force. It is a kind of weak force of attraction that is known as van der Waals force of attraction will also be high, my dear students. And as you go from iodine to fluorine, the van der Waals force of attraction decreases. Therefore, the alkyl iodine will be having, iodoalkane will be having a higher boiling point. Is it clear? And one more important and the point you all have to know, students. See what happens. Yes, of course, you understood the order. Now, what if I write a compound like this? So this is, what is this? This is nothing but bromobutane, or specifically you can call this as 1 bromobutane, right? You have to number it like this: 1, 2, 3, 4. 1 bromobutane. Now the same compound, if I write like this. Now this is also, the molecular formula will be same, but what you can observe the difference is, this is a straight chain whereas this is branched one, right? And so students, what you have to observe is boiling point of any isomeric haloalkanes like this decreases with increase in branching. As the branching, for example, the same compound, what if I write like this? Uh, it's like for example, here only you can observe CH3, just a minute. So in these two you can observe the example, one is a straight chain and the other one is a branch chain, right? So branch, what happens when the chain gets branched? You can see the students, the surface area decreases, right? When you see the branching, see the surface area how much it has occupied, and the branch chain, as the branching goes on, for example, if a compound is like this, still more branched. So now you observe the surface area has decreased, right? So as the surface area decreases, what happens? What you understood, the van der Waals force, what we call the van der Waals force also decreases. Is that clear? So as the branching increases, what happens? The surface area will decrease. As the surface area decreases, what happens, dear students? The van der Waals force of attraction decreases, and as the van der Waals force of attraction decreases, the boiling point also will decrease, and therefore I tell you, the straight chain will be having high boiling point compared to branch chain. Is that clear? So we have discussed a lot of physical properties and more to discuss about this chapter, dear students. So in the further coming sessions, please follow the teacher app, all the live videos and all the recorded sessions and doubt clearing sessions. Follow each and every materials that is given to you, provided to you, for the better understanding of each and every concept, and in detail and in-depth understanding. Definitely platform is going to help you in all the ways, my dear students. So in today's session, we discussed one of the best various methods of preparing haloalkanes and haloarenes, also the most important physical properties that are shown by haloalkanes and haloarenes. Next session, I'll be very much eagerly waiting to give in-depth knowledge about haloalkanes and haloarenes, and I hope you'll also be waiting for the more and more sessions. And all the very best, my dear students. Follow each and every concept, and yes, you have to practice well along with listening to the concept. And yes, thank you all. Thank you once again.